Welcome, intrepid physicists. My name is Mr. Gopal, and let's work on work today. And so, for a little bit of background, we are picking up in our unit on energy. All right, and this is day 12. The objective is to define work and identify the units of work, and then solve some simple problems involving work. And what you'll see is eventually we're going to complicate the situation a little bit more and more as we go on. But for now, we'll keep it simple. The idea that they give at the beginning of the lesson is a roller coaster. All right, so hopefully we all know how a roller coaster works. A bunch of people at an amusement park get in roller coaster cars and they are taken up to the top of a hill usually. All right, and if we're thinking about forms of energy and conversion of energy and accumulation of energy, what's going on as we go up that to the top of that hill is, by virtue of our height and the mass of the people and the car and acceleration due to gravity, we are storing up potential energy until we get to the top of that hill. Then as we go over that, that potential energy is converted into kinetic energy. And we go through a fun roller coaster ride. We probably go down a hill, maybe we go through a loop-de-loop and a corkscrew, changes every time for every different roller coaster, right? But we have many energy conversions. Let's say we went down a hill. At the bottom of that hill, all of our potential energy would have been converted into kinetic energy. And then as we go up another one, some of that kinetic energy will be converted back into potential, and so on and so forth. Final thing I'll say about that, we also have the situation where there's heat energy dissipating. This is not a conservative system, meaning all of the energy is not conserved between those two forms, potential and kinetic. All right, heat energy from the friction between the wheels and the track is going to dissipate out and reduce the total energy in that roller coaster car system. All right, that is a little bit of a review of before. Now we're going to talk about work. And as they say in the slide here, while the coaster is being towed up, it's having work done on it. All right, and that is because it is being taken from one place to another. Allow me to illustrate myself. So if I take this textbook that I have and I hold it up here, as I'm talking to you, it's requiring energy of me to hold this. I'm exerting an upward force on the bottom of the book in order to hold it up in front of the screen. All right, and if I did this for a long time, probably my arms would start to get tired. But let's say that it's not moving at all. You can probably see it just like hovering about a little bit. But let's say it wasn't moving at all. The implication there is that I haven't done any work. And now I'm going to illustrate why. So when we talk about work, there are more factors than the amount of force that goes into an object. Picture this book now. It's off screen, but it's on my desk. So picture it on a table. And so there's the table. Black horizontal line. Actually, I'm going to undo that. Let me change the color for the book so it's a little easier to see. Okay, here's my book. And if we're diagramming these forces on the book, we know that there is a force of gravity pulling the book towards the earth. There's also a normal force equal in magnitude to the force of gravity and pointing in the exact opposite direction. All right, perpendicular to the surface, and the surface is level. Okay, so it's parallel with the ground. So in this case, they're equal and opposite. If this table happened to be on an incline, the normal force would be 90 degrees from that incline. It is always perpendicular to the surface. And I can label these two. Here's my normal force, capital F sub capital N, and then capital F sub lowercase g for my force of gravity. All right, but the book is at rest. So even though there are forces acting on it, there is no work being done on this book because it is not moved from one place to another. Let's say I also label this as my initial position. All right, and I'm going to leave the situation as that right now because we've come to an interesting place where we realize that the physical definition of work, not the one that we use every day, is work is force multiplied by distance. All right, and it's even a little bit more detailed than that because the angle of the force determines the magnitude of the force acting in the direction of the distance, okay? We'll talk about that more later. I don't want to get into that right now because I'm going to overcomplicate the situation, and we want to get a simple working definition for right now. Okay, so force multiplied by distance. And so in other words, if an object has a force or forces acting on it, but it is not displaced, no work is being done on it. So in the case of the roller coaster, yes, work was being done because you were carried in that car, or that car was carried up the track from the bottom to the very top of it, okay? Before then the pulley system stopped and it was allowed to just, using the force of gravity, it was allowed to just go down the hill again, all right? And we had all those conversions of energy that I was talking about before. In this case, we have forces acting on these books, this book, but these forces are not moving the book anywhere. So in order for us to get a situation where work is being done, we need the book to be displaced. Let me first write the equation. It's going to go along with this scenario. Sorry, I didn't mean to do that. Click out of this. So our working equation, no pun intended, for work is capital W for work equals force times distance, all right? And so we've got that here. And now, let's say that I move this book over here, okay? So let's say that I apply a force on the desk. Maybe you can hear it a little bit, but I just moved my book over about half a foot to the right. And let's say that I want to illustrate that over here. So I'm going to grab my vectors again. Let's make a different colored vector for the work just to distinguish it from these forces that are not moving it. So I apply a force this way, and it's strong enough that I can move the book over, all right? So since it's me, the actor, doing that force, I'm going to call that F sub APP for an applied force. And let's say over here on the right is my final position. There we go. Okay. And so we know right here, I'm marking exactly from the center of mass, or roughly from the center of mass of the book here and here, that our book has been displaced about that far, which we can represent as delta x. Okay. And so we've got all the situations diagrammed out. So let's say this is a 10 Newton force. All right, I'm gonna label that a 10 Newton force. And let's say this gets displaced 3 meters. So I can plug these values in here. I can say 10 newtons times 3 meters is going to equal 30 Newton meters. Now, we can also convert Newton meters into a new unit, and we call that unit joules. And those are represented by a capital J. Okay, so a few things to recap right now. All right, we have a new formula. All right, we also have a new definition, and this is one of the first times I think in physics where there's a notable difference between the way that we talk about, or the way that we utilize a word, I guess you could say, in physics versus the way that we tend to utilize it every day in life. All right, and that's that work has to include distance if it's going to be non-zero. All right, you could picture various situations in your life. If I reach over and I push on my fireplace, you know, it is built into the foundation of the house, so it's not going anywhere no matter how hard I push. All right, and that's causing, like, I'm having to put a lot of force into it, but I'm not doing any work because that fireplace is staying exactly where it is. All right, so here are a few other considerations I'm going to leave you with, but we are going to continue this in future videos. Okay, so don't despair. Another consideration to take into account is that the force, or sorry, the angle of the force with respect to the direction of displacement determines the magnitude of the force. All right, that sounds really weird. First, I'm going to clean it up. I'm going to put it in simpler language. All right, if I push this directly in the same direction as the motion, all right, then the displacement and the vector of the force are the same, all right? However, if I were to be pushing this up the whole time, I wouldn't be contributing to the work that's going on. Let's say that I was pushing it up with my right hand negligibly, so it's not coming off the counter, but I am exerting an upward force on it. At the same time, I'm pushing it with my left hand over. My left hand is doing work, my right hand is not. You might think to yourself, well, why not? It's moving. You're using both your hands. But note that we have in our diagram a few different forces, that are not contributing to the work in this situation either. Since gravity is operating at a 90-degree angle to the direction of displacement, and since the normal force is also operating at a 90-degree angle with respect to displacement, they are doing zero work on the book, all right, when it moves from xi to x sub f, all right? And so we can add a little bit of detail to this situation. If we're talking about the work done by the applied force, the angle, so I'm just going to add FAPP in there to make more detail. The angle between sorry about my handwriting, the angle between FAP and change in x equals 0 degrees, okay? However, the angle between these two forces, the angle between both Fn and Fg and change in x is 90 degrees. And so what I'm going to show you that hopefully ties this all together is we can add a little bit more detail to our work formula now that we have the basics. And that detail, I'm going to write in purple down here, that detail is that W actually is going to equal F times D cosine theta. And this cosine theta is the angle between the applied force or the force in question. So actually, let me just reduce that to F and change in x or displacement. Okay. And so if we think about that a little bit more, what's going on is that I'll explain this. So I can calculate the amount of work for every force in a given situation where an object is moved or not moved, for that matter. I can take all three forces here and I can calculate independent amounts of work for them. All right, for the normal force and the force of gravity, that would be 0, as we said, because they're not contributing to the movement of the book. All right, the applied force, as we calculated, is 30 joules. Let me illustrate. If I'm calculating the work done by gravity here, let's say that, then I'm multiplying Fg times D cosine theta in full knowledge that the angle that in question that's represented by theta is 90 degrees, because that's the angle between the force of gravity and the direction of the motion. All right, so if I pop in, let's say that this is a 10 kilogram box, our book, And let's also say that the force of gravity is 10 meters per second squared, or acceleration due to gravity, sorry, is 10 meters per second squared. If I plug those in, I'm going to get 10 for my mass. That's 10 kilograms times 10 meters per second squared times 3 meters times the cosine of 90 degrees, all right? This is just for gravity again. And so just to clue you in on everything I did, I broke down F sub g into mass times A sub g, or acceleration due to gravity. All right, and that's where I get my 10 kilograms and my 10 meters per second squared, respectively. For d, I plug in 3 meters. For the angle between the force of gravity and change in x, I plug in 90 degrees. And since I take the cosine of that angle, this becomes 0, all right? And then when I multiply the rest of it, I'm going to skip writing the units this time. What do I get when I multiply 10 times 10 times 3 times 0? Well, it's quite simple. I get 0 joules. So the work due to gravity is 0 joules, all right? And this would be the same calculation for the work done by the normal force. And so getting back to this, all right, couple things to bear in mind as we traverse work. Number one, in order for work to be done, an object has to be displaced. Our formula for this is force multiplied by distance, but if we add detail, we know that it's force times distance cosine theta, where theta is the angle between the force and the direction of motion, all right? We'll start to work with more complicated angles than 0 and 90, but for now you can see if I'm doing this, we know that the cosine of 0 degrees also happens to be 1. So in this situation, we can see why I didn't even need to multiply the applied force and change in x times cosine theta, because I knew I would just get the same number, all right? In other words, whenever the angle between the force and change in x is 0, then it's just going to be F times D, because those are operating in the exact same direction. Whenever the angle is 90, the amount of work done by that particular force is going to be 0. And we'll start to look at more complicated situations soon. Thank you very much. I hope this was very helpful for you, and I hope to see you soon.